Okay. Very good. So in this last lecture, what I want to do is conclude the discussion of some aspects of six-dimensional vacua. We talked this morning, first of all, about anomaly cancellation in 6 dimensions, which, as we found, gives us very strong constraints. At least if the number of tensor multiplets is less than 9, then this space of possible supergravity theories is bounded. There's some fixed limit to how many of them we can have. And then when t is greater than or equal to 9, we have some infinite families of supergravity theories, which we can't rule out. So today, in this second lecture today, I'm going to talk about two kinds of constructions from string theory, heterotic and F theory. And the idea is the following. So in a lot of work on string compactification, you take some higher dimensional theory, you take supergravity or F theory or whatever, plus some gadgets, and you compactify down, and you get some 4D, or in our case, a 6D theory. And so you explore the space of possible string theories and supergravity theories by putting in different combinations and going down. So I'll do that for these two kinds of string constructions. But what I want to focus on as well is the question of how we go the other way around. In other words, given some low energy data, can we go back and uniquely or close to uniquely identify what the stuff was that you have to put in the string compactification to get that vacuum? And what we'll find is that in both of these two cases, this mathematics of lattice embeddings that I keep mentioning will give us kind of the key to going from the low energy data up into string theory. And that'll be kind of a theme of these two constructions. So let's see if I can just jump to there. OK. So let's start by next talking about heterotic vacua. We did some intersecting brane models this morning. I left the data up there because we might need some of it again. Now we want to look at heterotic vacua compactified down to 6 dimensions. Yesterday we did heterotic vacua down to 8 dimensions. Or maybe on Wednesday we did heterotic vacua down to 8 dimensions. And in that construction, we were compactifying on a T2. So the key thing was understanding, first of all, Wilson lines, which could break the symmetry, or the lattice embedding, which the lattice that we were compactifying on, which could give us extra enhanced symmetries. So going down to 6 dimensions, we can now compactify on a K3 manifold, which we've talked about in a number of different ways. And this gives us more complicated possibilities because we can now put instantons in our gauge field, and that will enhance the range of possible things we can do. So in terms of this classification we started today with, all these models are going to have one tensor multiplet descending from the 10-dimensional supergravity B mu nu. There are limits where we take instantons to shrink to points. These become 5 branes. 5 branes carry B mu nu, and therefore would contribute extra tensor multiplets. But I won't be talking about that limit very much today. So let's see what we can learn about the compactifications of heterotic with instantons by remembering a couple things from what we've learned so far. In 10 dimensions, remember, we discussed in combination with the Green-Schwarz mechanism that the curvature of the B field, the H flux, has to have 2 terms in it. It has to have a Chern-Simons term from the Yang-Mills theory and a Chern-Simons gravity term. And that leads to a Bianchi identity, which is that DH is the trace of R wedge R minus trace of F wedge F. And if we compactify on K3, there's going to be an integral of trace of R wedge R. And since the integral over K3 of DH, a 4-form over that K3 has to vanish, it's going to force us to have instantons. So from this point of view, if the integral of DH vanishes, then these two integrals have to equal each other. And we can write that in terms of various characteristic classes. So the second Chern class, which is essentially the instanton number, which is 1 over 8 pi squared integral of F wedge F. This is equal to 1 over 16 pi squared trace of R wedge R, which is minus a half of another characteristic class, which on K3 is equal to 24. You'll notice I stuck in a factor of 2 here. Here these guys are equal, and here there's a difference by a factor of 2. That's because the standard notation for this is in the fundamental representation, whereas the standard notation for this is in the adjoint representation. And we can use our handy table over here that let's see, this is SO. This is an SO group, so it's in the adjoint of SO, which is right here. So the relationship between trace R squared in the adjoint and trace R squared in the fundamental is we get a factor of 2. So those two conventions are related by our handy table. So anyway, that tells us that if we compactify on a K3, we're going to need to have 24 instantons in the gauge group in order to get a good supersymmetric solution. Any questions about that?
What's this P1? I'm just seeing C2 and P1.
C2 is a Chern class. These are characteristic classes. P1 is the first Pontryagin class.
And that's the dimension with the complex P form?
It's a 4 form. Yeah. It's just this, basically.
So what's the 1 form P1?
Because these guys go up by 4s. Just like these guys go up by 2s. Second Pontryagin class is an 8 form. Other questions? OK. So I'm going to look at, obviously, it's a rather complex thing to look at the full space of instantons on K3. And there's a lot of literature on that. I'm not going to do the completely general case. I'm going to focus on a simplified version of the set of configurations with instantons, which are essentially these magnetized brane models. The idea is, so we know that if we take the heterotic string now with SO32 or E8 cross E8 as the gauge group, we need to put an instanton number on K3. And we're going to implement that instanton number by turning on U1 fluxes in various U1s within the SO32 on 2 cycles. And again, in the type 1 language, this is something called a magnetized brane, which is essentially T-dual to an intersecting brane model. Miriam has told us a lot about intersecting brane models this week, and we talked about some simple intersecting brane models in 6 dimensions this morning. The idea is if you take a torus with a diagonal brane on it like this, and you T-dualize it in the vertical direction, then you get the dx turns into dA because fx goes to A, and that becomes flux. So diagonal intersecting branes turn into branes with fluxes in the T-dual magnetized brane picture. Now, this is a little more subtle than it might seem because we can't necessarily directly do T-duality on a K3. We can take this orbifold limit, and we have something which looks like T-duality, but I'll comment a little bit more on that later. But heuristically, we can think of this as a sort of T-dual to an intersecting brane model. It gives us good intuition for what we're doing. So another way of saying this business that we have to have these D-branes we can think of in the type 1 language. We talked this morning about orientifolds, and Miriam has talked about orientifolds. If we have an instanton on a D9 brane, right? So previously I was talking heterotic language. Now I'm going to talk type 1 language. Both theories have this gauge potential and gauge field on it. In the language of type 1, we have D9 branes. And if there's an instanton on the D9 brane, that carries D5 brane charge, right? Just like the dx here carries, if this is a 1 dimension, the dx carries brane charge in the 2 dimension. Similarly, an F carries P minus 2 brane charge. And F wedge F carries P minus 4 brane charge and couples to the appropriate Ramon field. So F wedge F couples to C6 hat. There's an analogous coupling. So just as F wedge F essentially gives you P minus 4 brane charge, R wedge R, for a brane wrapped on a compact manifold with R wedge R, does the same thing. And the same thing is true for O planes. So if we take the O9, which we know has 16 D9s to cancel its charge plus the images, and we wrap it on K3, each D9 which is wrapped on K3 gives us a D5 brane charge with the minus 1 D5 brane charge. Each O9 wrapped on K3 is going to give us minus 8 D5 brane charges. You add those up, you get 16 plus 8. We need 24 D5 branes, which are the instantons on the D9 brane, to cancel that contribution to essentially a tadpole. Okay, so this is just a different way of saying the same thing I calculated in the previous slide using the Bianchi identity. It's a different way of seeing why we need instanton number 24 from the brane point of view. Questions? So one of the nice things about taking this point of view, which makes it a little more flexible in some ways than the intersecting brane construction, which is generally done on the orbifold, is it's a little easier to do on a general K3 where we don't impose an orbifold limit. So we're going to now look on a general K3 and not on an orbifold limit, like we did this morning. And this class of theories where we just turned on U1 fluxes on a K3, this was actually really one of the first lower dimensional compactifications of string theory studied. Green, Schwartz, and West looked at this in the early days as one of the first, this was really the first paper about six-dimensional supersymmetric theories of gravity and anomaly cancellation. Precisely this class of theories was what they were looking at. But I'm going to go just a little further here in analyzing what we can say about that class of theories. So are there any questions about what? Yes, question.
K3 can also be thought of as an elliptic vibration over a sphere with 24 singularities.
That's right. We did that last time when we were talking about F theory. We're not going to use that presentation today.
So this 24 has nothing to do with that.
I think you can relate them actually. I think that you can relate those two things. I don't see a really clear, precise, and simple way of saying that relationship, but I think that there is a relationship. That's an interesting observation. Good.
Those relate to the total cohomology, right? The 0 forms and the 2 forms and the 4 forms give you 4.
That's correct. Although, yeah, there's probably more to be said than I'm saying, but I don't see a simple, clear statement of it. But I think those things are connected. Good. Okay. So let's just talk a little bit more about the general K3 rather than the orbifold K3. K3 is a complex surface, so it's a complex two-dimensional space, and as such it has a complex structure, basically DZ1 wedge DZ2, which is, this is a Hodge decomposition into holomorphic and anti-holomorphic. There's a complex structure, which is a holomorphic two-form. And this satisfies a couple of equations. If you wedge the holomorphic two-form against itself and integrate, you get 0, basically because you're just wedging DZs. And so they can't turn into a volume form. But if you take omega wedge omega bar, then you're wedging DZs versus against DZ bars. This is proportional to the volume and is greater than 0. So if we write omega, which is a complex holomorphic two-form, as a real two-form plus an I times another real two-form, so these are now elements of the real cohomology, when we take the intersection form on those guys, this first equation, right, omega wedge omega, that's the imaginary part of this is just I x dot y. That has to vanish. So x dot y vanishes. And the real part of this is just x squared minus y squared, which must vanish also. So x squared equals y squared. So x dot y vanishes, x dot x and y dot y summed will give us this, because this is x minus I, x plus iy dot x minus iy, which is x squared plus y squared, which is positive, and therefore both x squared and y squared are positive as elements of the two cohomology. Furthermore, there's a Kähler form measuring volumes on this thing, which is a 1-1 form. We'll measure the volume of any two-cycle we want to integrate it over. And this satisfies, first, the condition that j wedge omega vanishes, which means that treating this again as a two-form, j dot x and j dot y vanish. And integral of j dot j, again, is proportional to the volume, so j dot j squared is greater than 0. Now, the important thing I want to take out of this is that we have constructed, these are the moduli of the K3. There's the complex structure moduli and the Kähler moduli incorporated into this x, y, and j. And these guys define a positive definite three-plane in the second cohomology, because x squared, y squared, and j squared are all positive, and all three of them are orthogonal to each other. So this thing these three vectors have to live in H2, which, remember, is R319 if we take coefficients in R. So these guys span a positive definite three space, and everything else has to be perpendicular. Sorry, everything else that's perpendicular to those is going to have to be negative norm. So these kind of pull out the positive part of this R319. Okay? So what does an instanton look like? So again, we're going to turn on an instanton by just turning on fluxes. So we can think of those fluxes as like the fluxes on 16 U1s, which are in the center of SO32, right? SO32 we can think of as having, it's like the 16 branes and their images, and each brane has a U1 on it, and in the SO32 language, that's 16 copies of this 0, 1, minus 1, 0 guy. And we're going to turn on, much like brane stacks, we're going to turn on flux stacks. We're going to turn on NA fluxes, FA, where each of these fluxes has just been normalized. So the flux is F. I'll normalize by a factor of 2 pi to get rid of those 1 over 8 pi squareds. So that F dot F is an element of 2z, and therefore these F's are in a lattice. So really what I want to do is put these F's, normalize them so that the fluxes live on the integer lattice of K3, which, as we discussed before, is gamma 319. So our fluxes are going to live. Fluxes in the U1s, which live in the SO32, and we can turn on, say, N1 of the first kind of flux, N2 of the second kind of flux. So these are going to be choices of 2 cycles around which this flux is wrapped. Now, the Tadpole constraint, which is this coming from this, which we just derived in 2 ways, both from the type 1 point of view and from the Bianchi identity, saying that the total instanton number is 24, in the language of these little f's, which live in the gamma 319, says that if we sum over all the stacks, NA times FA dot FA, that's just the F dot F here, has got to be minus 24. So the trace is the sum over the ends, right? And then FA dot FA is just the intersection form of the flux 2 form with itself, which is just this instanton number. So we basically have a bunch of elements in the lattice FA which add up with multiplicities to minus 24. It's good that it's negative because we got rid of all the positive stuff, and the supersymmetry constraints tell us that FAs have to be orthogonal to the complex structure and to the Kähler form. So they are orthogonal to this little 3-plane that we found of moduli, the complex structure and the Kähler moduli. So there are 2 ways to think about this. One way to think about it is we could pose the problem of fixing the moduli, choosing omega and choosing j, and then asking what fluxes we could turn on. And that's tricky because as omega and j move around, we would have different kinds of fluxes that we could turn on. So that would be a hard problem if we first fixed the moduli. Instead, since I'm interested in understanding all the possible things we could get, I'm just going to say let's choose any fluxes we want, and then for any choice of fluxes, there will be some choice of moduli which may be compatible with that. And in fact, since these f's, so if the f's are chosen to be negative definite, so if all the f dot f's and fa dot fb's live in a negative definite sublattice of this thing, so if the f's define a sublattice which is negative definite, then there's always a perpendicular positive definite 3-plane so that we can choose these moduli omega and j in a way that gives supersymmetry. There may be we may reduce the dimensionality of the moduli space for certain choices of fluxes, but for any choice of fluxes which live in a negative definite sublattice of gamma 319, there will always be some moduli which are available. So we always have some construction. Okay, so I'm not going to care from now on about those moduli. I'm just going to know that whatever fluxes I choose, as long as they span a negative definite lattice, we're going to be fine. We can find some moduli for which that works. So that's a valid class of models. There's some moduli space of models associated with that choice of fluxes. Questions about that? Okay. Not Okay. So the fluxes, Fa, generate some even sublattice, even negative definite sublattice, lambda, which is a sublattice of gamma 319, which characterize any given theory that we're going to see coming from this compactification. So the gauge group is just going to be un1 times un2 up through unk times SO32 minus the sum of the n's. That just comes from looking at our SO32 here, and we look at the commutant of this guy. The things which commute with this are going to be an SUN, N1. The things that commute with this are going to be an SUN2. And the residual stuff is going to be an SOM, where M is 32, minus twice N for each of the stacks that we've taken away, because you take 2 of the N M's in SO32 away every time you turn on a flux. So the gauge group is going to be a product of UN factors with an SO32. I'll just mention that since each of the F's, since the F squareds are even, sum over NA FA dot FA, this guy is even, so it means that we have at most sum of the NAs equals 12. Twice that is 24. 32 minus 24 is 8. So we always have SO8 or greater as a subgroup for all these constructions. Basically, that just means if we put a general instanton on K3, we're always going to have a residual SO32 gauge theory. A couple of technical points. I've included some U1s here. I'm generally avoiding U1s because there are some technical aspects of them. Some of these U1s are going to be anomalous, and then they pick up an extra degree of freedom from a B field, which is called the Stuckelberg mechanism, and then they go away and become massive. There's another subtlety, which is that when the F squareds are equal to minus 2, you can have a further enhancement of the gauge group. That's another whole interesting story, but it's a little subtle, and I'm not going to really go into it. Okay, so now we have some construction where our construction of a heterotic vacuum here, magnetized brain vacuum then, is given by a choice of fluxes which satisfy the Tadpole condition. And we can compute, yes?
Why do you say F dot F is even?
Sorry?
Why is F dot F even?
We chose the normalization so that F dot F was even, so it lives in this even, gamma 319 is an even lattice, and we chose the F's to live in that lattice. So it's just a normalization convention. If you go back and trace it through carefully, there's a unique normalization convention so that the F is a correct element of gamma 319. Basically, I want the F's to be in gamma 319 with the usual even inner product. So in this case, we can compute the matter spectrum in several ways. So I think a couple days ago, Miriam went through a nice conformal field theory calculation of the matter spectrum. You can do that. In this case, you can actually just use an index theorem because you're computing the number of chiral fermions in a given background, a given gauge field background. So it's really just the index is associated with trace of F1 minus F2, wedge F1 minus F2, where F1 and F2 are the two fluxes that are the two fluxes that are relevant. So you can sort of see that coming out in these various things. You get a minus 2 plus minus some flux from the index theorem. So you can get that in either of these ways. These numbers should be fairly familiar. If you get a UN, just like in the intersecting brain model, there's always going to be an adjoint. You have intersections, NA and B. These are like the intersecting brains. Again, you're always going to have these FAs and FBs between two different fluxes parameterizing the kind of matter that you're going to get. So I'm not going to go through the derivation of this. These are very similar in spirit to the table of matter multiplets that you will get in an intersecting brain model, but the numbers are a little bit different. But these can be derived in several ways.
Is there anything that the index misses in terms of matter?
Not in this class of theories, but you'll notice that the kinds of matter here is fairly restricted. We're only getting adjoints, bifundamentals, antisymmetrics, and bifundamentals with the SOMs. One of the things that we'll see when we go to F theory is that you can get all kinds of other complicated representations, which I don't know how to see from this kind of language.
So there's no analog of the 40 case where the indices sort of calculate
I don't think so. I think in 4D it's a little more complicated because you have, I'm not sure. Yeah, we should talk more about that. But I believe, I mean, here certainly all these can be calculated by the index theorem. So it was checked in this original paper by Green, Schwartz, and West that all the anomalies cancel for these models. So basically we can now classify all the magnetized brane models. What we need to do is look at this table, and we can choose any model we want by basically choosing. So I define MAB to be the intersection of FA and FB. That defines a lattice. So basically, if we choose a lattice compatible with the Tadpole constraint, which is that the diagonal, basically with the multiplicities of NA, is minus 24, we can choose any lattice we want. That is intersections of the FAs and FBs. And as long as we satisfy this Tadpole constraint, we can ask, is this a good model? In order for this to be a good model, there has to be a lattice embedding, an embedding of the lattice lambda into gamma 319. So you remember early on in these lectures, I talked about these Nikulin embedding theorems, which give necessary and sufficient conditions for the embedding of a lattice into an indefinite signature even unimodular lattice. And there's a slightly different set of theorems than the ones that I mentioned previously, which show not only that such an embedding is possible, but that it is unique with certain conditions. So with Vijay Kumar, we showed that basically for every possible lattice which you could get, which satisfies this condition, the embedding is possible. It goes right to the edge of the applicability of the Nikulin embedding theorems. The maximum dimension of the lattice you could have is 12, because each of these has to have at least 2. So the biggest thing you could have is a 12-dimensional lattice with 12 minus 2s. And Nikulin's theorem precisely allows that, but not one more. So there's something kind of magical happening there, which I don't fully understand, which is that this goes right to the edge of what you're allowed to embed and not further. But it is the case that anything you can get here is automatically embeddable. So all these models are possible. And furthermore, we now see, given some low energy data, that is this data, you can read off the inner products of the Fs. That gives you the lattice. And then you find your lattice embedding, and that identifies the string theory data you need to define your model. So that's this map I was talking about, going from low energy data up to the string theory data through a lattice embedding. A couple comments about this. So this gives us, if you do the more general, at the first part of this morning's lecture, I talked about this general classification of all possible models which are constrained by these anomaly conditions. So we can go through and actually make a list of all possible models with a gauge group of the form SO2M cross SUN, etc., where actually we also restrict the kind of matter to the fundamental bifundamental, the things that appear on that chart. And you can ask, what fraction of those models do we get in this approach? And the answer is you get almost everything. So if you look at the full set of anomaly-free models with gauge group SOM cross SUN, and you use this heterotic construction, or magnetized brane construction, you get all of them, except if you have one SUN factor, there's this model, which you don't get. SO8 cross SU24 with 3 antisymmetrics, and then various relatives of this where you have more SUN factors. That's the only one you don't get. So that's a kind of a funny model, which let's remember for later. That's one model which we can say is anomaly-free. We don't know how to realize it in string theory. You can generalize this sort of approach to E8 cross E8. I've only talked about abelian bundles, not non-abelian bundles, so there's a whole more complicated story. There's a huge literature on more general bundle constructions. One more general approach to this, which then tries to relate it to F theory, was this Freedman-Morgan-Witten approach, and there's a whole literature there, which I won't delve into. Something to emphasize is we're talking about different gauge groups here, but these are all living on the same moduli space. So we move around in the moduli space. You can increase or decrease the size of the group through Higgsing. So this is a bigger class of models than we got this morning using intersecting brane models on the orbifold K3, but it's still sort of limited. And in particular, if we look at the full set of anomaly-free models that we can list from our analysis of this morning, there are lots of models that it doesn't seem to see. First of all, we're fixed at t equals 1. If we go to singularities and singular instantons, we can get to 5 branes. But in particular, we have somewhat limited matter representations, as we said. So we'd like to get more. Let me make an observation. This morning, we talked about the simplest intersecting brane model on K3. and we found this model with an SU8 gauge group, you'll notice that that model does not appear here. All these models have SO at least 8. So even though in some moral sense there's a T-duality relating this type 1 construction on K3 to the intersecting brane models on K3, there's not a precise match between the sets of models you can get. That intersecting brane model with an SU8 gauge group doesn't appear here. So there's a couple reasons for that, a couple things which affect that. One of them is that because of the orbifold points, the T-duality story is a bit subtle. There's this model that Jamon and Polchinski looked at where you have instantons sort of trapped at the singular points. And the models I mentioned this morning where you use fractional cycles can relate to those in some sense through T-duality. But for these kinds of models, we don't have a precise match between the two sides of the duality. And that's partly because of the limitations of T-duality, and partly because, unlike in what we found in 8 dimensions, it is not in general the case that two dual descriptions of the same set of vacua will give you precisely the same boundaries on that set of vacua. And I think I have time to tell you another 4-dimensional anecdote. I've threatened to tell you 4-dimensional anecdotes occasionally through the lecture in lieu of an actual 4-dimensional lecture. So let me give you another brief anecdote. And this has to do with flux compactifications. So this is an example of a situation where it seems like you have two constructions which should be dual to each other, but they give you different sets of low-energy theories, and we don't quite know how to connect them. Again, in 8 dimensions, we did heterotic, we did F-theory. We got exactly the same moduli space. Everything fit together beautifully. That's not the case in lower dimensions. So in type 2b, there are these flux compactifications. This nice paper of Giddings, Kachur, and Polchinski, and various followers. Basically, you can turn on fluxes. There's a tadpole, which is an integral of f wedge h. So if you have an orientifold, and instead of canceling the orientifold with d-branes, you cancel the orientifold charge with f wedge h. And then there's a contribution to the superpotential, which looks like integral of g wedge h, where g is, g wedge omega, where g is equal to f plus I h. I think f plus I phi. Make sure I get the thing roughly right. Let's go f minus phi h. Haven't worked on this for a while, so I've forgotten all the signs and things. So there's some superpotential, and you can construct various solutions. So the solutions are given by dw equals 0, which implies this imaginary self-dual constraint, g equals I star g. And this gives this famous class of type 2b flux vacua. So we can compactify on some Calabi-Yau, turn on fluxes, and we get a picture where basically when you turn on the fluxes, you fix then the complex structure moduli by these equations. This imaginary self-dual constraint fixes the moduli, so you get this so-called discretium of various vacua. And Ashok, Douglas, and Denef talked about sort of the distribution of these things. So there's a nice distribution on the complex structure moduli space. And again, we talked a little bit this morning about when classes of vacua are finite versus infinite. There's no proof, as far as I know, that you get a finite set of vacua here, but there is a mathematical argument that the integral of the density measure is finite. So unless something weird and pathological happens, which people don't understand, you should get a finite number of discrete vacua here. So there's some finite discrete set of vacua here that you get by a 2b flux compactification. Similarly, you can do a very similar story in 2a, which Oliver and Giryevitz and Shamet Kachru and I looked at, among other things. You go through a similar story. It's a little more complicated. Here you can solve both the complex structure and the Kähler moduli. And here you get infinite sets of vacua. So two constructions which naively look like they should be T-dual. There should be some mirror symmetry relating type 2b to type 2a, which is really T-duality on a toroidal fibration over a three real dimensional base. There should be some T-duality relating these, but the sets of vacua are very different. And this kind of fits into this general kind of question I've been asking along in these lectures about what theories are allowed in supergravity and what theories are allowed from string theory. If we look at these two constructions, adding an H-flux, among other things, turns these things into gauged supergravities. So, we've been talking about the fact that if we come down from 10D down to 4D, we're going to get a U1 to the 12 coming from the G and the B on the compact directions. This would be on a T6. So we get various U1s. Some of them come from the B part, and some of them come from the G part. We can break them up into two groups, Z and X. And if we turn on Neveu-Schwarz fluxes, we get a non-trivial non-abelian gauge group structure here. So the commutator of the Z's, get the right place. These end up looking like H, J, K, Z, K plus F. If we turn on H-flux and we turn on some geometrical twisting, which is incorporated in this guy, which we'll call geometric flux. This is just like twisting a torus by gluing it to itself with an SL2Z shift. If we turn those things on in, say, type 2A, then we turn on a non-abelian symmetry in these guys, which gives us a gauged supergravity. And part of this happens when we do these flux compactifications. If we do T-duality, then X and Z exchange roles. And so we can turn on a different set of these guys. So from the type 2A point of view, we can turn on structure constants here, here, and here. While from the type 2B point of view, we can turn on structure constants here, here, and here. Now, what happens if you look at the low energy theory? You could imagine turning on structure constants in all these places. But from the point of view of the string theory, these would correspond to some kind of non-geometric fluxes. So this is something that with Jesse Shelton and Brian Wecht, we looked at, and lots of other people have looked at these too. But in particular, this is an example of a situation where in this big low energy space, we have these gauged supergravities where we could, in principle, turn on any of those fluxes. And we don't know any inconsistency to turning on those fluxes. There's infinite numbers of theories that we can get by turning on different fluxes, and we could, in principle, try to solve them, although it's not clear that solutions make sense. Pieces of that come from 2A, pieces come from 2B, but this full set of theories is much bigger than what comes from either 2B or 2A alone. So that's an example of a situation where two dual descriptions give us subsets of vacua. So where's my green marker? So if we take that big space of things where we've turned on all the gaugings, 2A is over here, and 2B is over here, and they don't even intersect except, well, they intersect when those things are all turned off. So there's some intersection there where, for instance, we just have an intersection on a torus. So that's an example of this issue which I wanted to bring up, which is that just because two descriptions are dual doesn't mean they give you the same set of vacua. There might be something you can turn on in one description which you don't know how to turn on in the other description in the UV. And so I just wanted to bring that up in connection with this picture where the IBM model gives us an SU8, which we can't see in the ostensibly T-dual intersecting brane model on the K3. Any comments or questions on that? Oliver?
So for the ones that you can realize in both of these models, do you think those are literally dual to each other? Two descriptions of the same physics?
Sorry, you mean in the intersecting brane versus magnetized brane?
Yes. Or are they two distinct?
They seem to be disjoint.
Non-dual descriptions of the same low energy physics?
They seem to be disjoint, just like those guys are more or less disjoint.
So you have more than one description of the same low energy Lagrange?
No, disjoint, I mean that there's no, I don't know any theories which you can get both ways.
Oh, you can. They're not.
I think they seem to be disjoint sets, yeah.
So that flux is in principle it comes from
You mean in string theory? Well, in string theory, in principle, you can turn on these in the 2A description and these, say, in the 2B description. but we don't have any UV complete picture where we can turn on both. We don't know how to geometrize those. Okay. Any other questions about the heterotic type 1 magnetized brane construction story? Yeah.
So this fact that we can have, once we turn on fluxes, these two, descriptions, in spite of being T-dual,
right,
have different low energy theories. This doesn't come up in higher dimensions. Why?
Well, we just found it in 6. We didn't see it in 8 because 8 is very beautiful, and the only 2 ways we have of describing it give us complete descriptions of the same moduli space. Below 8, it starts to happen. Okay, let's do F theory in 6D. So, as we'll see, F theory gives us a very nice way of describing a very large class of theories, which matches very nicely with our discussion this morning of anomalies. So in F theory, we want to compactify on an elliptic Calabi-Yau with a section. So X here is at a threefold, and B is a complex surface. So we have to do a little bit more geometry to know what we're talking about. In the case of 8 dimensions, B was just a sphere. So the only codimension 2 things on a sphere were points. We need to have a little more notation to deal with complex surfaces as our basis. First of all, we need a definition of something called the canonical class. This is basically the maximum wedge product of the holomorphic cotangent bundle, which really just means it's a wedge product of dz1, dz2. It's an element of H2. And this is essentially a measure of the total curvature of this space in some sense. For a Calabi-Yau, the canonical class vanishes, and a manifold is Calabi-Yau if and only if its scalar and its canonical class vanishes. So the canonical class and the other gadgets we're going to talk about in this context are things called divisors, which are basically linear combinations with integral coefficients of algebraic hypersurfaces, meaning things defined by, you can define if you define a Calabi-Yau in a complex projective space by some equations, then a hypersurface is when you define one more polynomial equation that reduces the complex dimension by 1. So basically, if you have something defined in terms of a polynomial in z, w, and q, then if you set z equals 0, you're going to get a hypersurface. And these are always linear combinations of irreducible hypersurfaces. And the canonical class is such a thing. So for instance, the canonical class of the torus is 0 because this is just dz, and that thing doesn't have any zeros or any poles. It doesn't vanish anywhere. The hypersurfaces are defined by the vanishing locus of some polynomial. So this ties into what we were talking about in terms of this discriminant locus on the sphere. Remember when we did F theory on the sphere, we had some function, delta, defined in terms of f and g, whose vanishing locus was the set of points where the 7 branes were localized. We're going to do the same thing now in a more general context. We're going to have some vanishing locus for some polynomials on B, and this is going to define a divisor, which is our discriminant locus. Again, we're going to have a Weierstrass form. Discriminant locus is the places that vanishes. So we can generalize on the sphere, the condition for a good Calabi-Yau, or just one second, for a K3 compactification with an elliptically fibered K3 was that the base was a sphere with 24 points on it, each of which had a singularity. The same condition on a complex surface base is that the discriminant locus, which is a complex codimension 1 or a real codimension 2 thing, it's basically a bunch of, just draw the picture and it'll be clearer. Basically, we have now the base B is a real 4-dimensional complex surface, and the 7 branes are wrapped on complex codimension 1 curves like this. These are pieces of delta. These are the places where the elliptic fiber becomes singular. That always happens in a complex codimension 1 space. So basically, we have an elliptic fibration over this thing, and there's a set of places where this vanishes, and we're just defining this as some sum of hypersurfaces. And the condition that the full space be a Calabi-Yau is that the total vanishing locus, this thing delta, which is a sum of a bunch of curves, is going to be minus 12 times the canonical class. So the canonical class is a class, the delta is a class, and there's this relation between them. So did you have a question? How am I characterizing B? B is a complex surface. This is a class in H2 of B. This is the canonical class. It's a class which plays an important role. It's defined by this exterior product of the holomorphic part of the cotangent bundle. That's the DZ business. Yeah, behind you. Yeah.
Now you're saying that, so the Clavier threefold here, in sort of type 2 language, I would say it's some Clavier twofold.
It's not a Calabi-Yau. That's important. The base.
That's what I want to sort of.
Yeah. Here's the deal. In 8 dimensions, the base was a positive curvature thing. Yeah. Okay. That positive curvature thing, remember, had to have 24 points, which were singular. Those were the curvature in units of pi over 6. And we had to have 24 of them to get 4 pi. Now we have a surface. And basically every curve in that surface has to have that same property. It's got to be kind of a positive curvature thing with 24 singular points on it. So K is a class which measures the total amount of curvature you have. So I think it's clearest if I do this example. If we take P1, right, then K of P1, the canonical class, which is the same as C1 of the cotangent bundle, is minus 2 times a hyperplane, but a hypersurface. A hypersurface in P1 is just a point. So on P1, the canonical class is minus 2 points. Okay? And the condition, the Kodaira condition, says that minus 12 times K has got to be equal to the discriminant locus. Minus 12 times minus 2 points is 24 points. So the discriminant locus has to be 24 points. So this is generalizing that to a general surface. This surface is going to be much more complicated than just a K3. So classifying the bases is a little harder than it is to classify Calabi-Yau manifolds. For this reason, although I'm going to tell you a more or less complete classification of the bases you can use for F-theory in 6 dimensions, mathematicians really don't understand a complete classification of the bases for a compactification to 4 dimensions, which would involve a 3 complex dimensional base, which is a harder problem than classifying Calabi-Yaus. Yes, exactly. And this condition, this Kodaira condition, which basically says that, remember what happened on the sphere. Each singularity on the sphere kind of made up for the positive curvature of the sphere at that point. This condition that Kodaira wrote down is precisely doing that for a generic F-theory compactification. It was actually generalized by some other mathematicians, but it's the same thing in spirit. The idea is that K measures the curvature, and the discriminant locus, which is where the singularities are, those things are fixing up the curvature to give you a total space, which is a Calabi-Yau. It's just that equation.
And you might want that because we want to preserve supersymmetry.
We want that because we want to preserve supersymmetry. That's the only way we're going to get a supersymmetric vacuum in compactification of F-theory down to 6 dimensions in this case.
Yeah.
Good. Other questions? So we want to now look at bases which allow for discriminants which satisfy this condition. So let me just give you a couple more words. There are divisors, and then there are effective divisors. An effective divisor is one which is a linear combination of irreducible hypersurfaces where all the coefficients are non-negative. Basically, that means it's something you can write as an actual combination of hypersurfaces which can be realized by algebraic equations. It's not the negative of those. And then there's an irreducible effective divisor, which is one which is associated with a single irreducible hypersurface. The discriminant locus has to be associated with an effective divisor, meaning it's a real thing that you can actually get as a combination of hypersurfaces. And its irreducible components are the things that are going to give you gauge group factors. So this is a lot like what we saw in 8 dimensions, but it's just a little more complicated now because everything's happening in this divisor language, which just means curves, which are algebraic hypersurfaces on this thing. Delta is a sum over these irreducible pieces Ci, which give us non-abelian gauge groups through the Kodaira classification, which we talked about. Remember, we had this rule for how the singularity type of F and G and delta give us a gauge group. We do exactly the same thing here. We're writing down a general elliptic fibration, which could be in principle characterized by a Weierstrass polynomial F and G, we can actually forget about that and just talk about the discriminant locus delta. Delta has these pieces, xi, which give us non-abelian gauge group components. Nu is the multiplicity. So for instance, if we have n singularities all stacked up to get an SUN, then the multiplicity is n. As we saw yesterday, if we have an E8, we have to have 10 singularities stacked up to give us our E8, etc. And then there's some residual divisor locus, which are like the points on S2, which don't have non-abelian symmetry. They're just some points floating around, which don't give us additional gauge groups in the low energy theory, but are there to complete this equation. And this is a lot like a tadpole equation, right? This Kodaira condition, minus 12k, this is some positive thing. It's an effective divisor, and we have to add up effective divisors in delta to get that. And y is sort of the extra stuff that we throw in, which fills up that positive definite tadpole condition, but which doesn't have any non-abelian structure in it.
Can you maybe say a few words on the HI?
Yeah, these are irreducible algebraic hypersurfaces. So for instance, if I wrote locally, if I have a z comma w plane, if I write down w squared minus 5, that's not irreducible because I could write it as w minus the square root of 5 and w plus the square root of 5. So it actually looks like that. If I write down w equals 7, that's an irreducible hypersurface. So it's one that can't be written as a sum of two irreducible hypersurfaces. Okay?
So on the basis of them, those are your HIs.
Yeah. So in fact, I'm going to give you, yeah?
Was there a reason our divisor had to be convention 1?
That's where the 7 branes are wrapped. And the 7 branes are always going to be 2 less dimensions than the total. It's also, in the language of the geometry, that's where the singularity locus appears. And the equation that delta is really some polynomial locally. The equation that a polynomial vanishes is generally a complex codimension 1 condition. So really, this discriminant locus is just delta is some function of the base coordinates. If you have coordinates w and z locally, it's a function of w and z. And setting it equal to 0 is in general going to give you a codimension 1 curve. Right? Any polynomial equation is in general going to put one complex restriction. What's that? Unless you did something really, yeah.
What is the total order of the vanishing locus, like before the previous?
So it depends on what your base is if you want to write it as a polynomial. The Kodaira condition is the thing which tells you really, on P1, this was 2 points, and therefore this was 24, so we could say, okay, the vanishing locus is 24. This will be a little clearer when I do some examples. But basically, we want to do something like that. We want to say, okay, k has some particular thing, therefore delta has to be a polynomial which matches that in order.
But suppose if this is the general condition, then in the previous case, would we not have chosen instead of P1 some other surface whose k would be put in to calculate in the previous case?
Do you know any other positive curvature complex curves?
So the k essentially is measuring curvature?
Yes. K is measuring curvature, essentially. And it needs to have the right sign, or else we won't be able to build up a Calabi-Yau by putting things on it. So it's key that it's be a kind of positive curvature thing on the bottom. But it gets more complicated as we go to higher dimension. So the other thing which happens, which makes life interesting in the compactifications to 6 dimensions, is now we can get matter. Because if you have one curve where this elliptic vibration becomes singular, C1, and another curve where it becomes singular, you can have a worse singularity at the point where these things intersect. So for example, let's say we have 2 coordinates z and w, and we have an an minus 1, meaning an sun, associated with this curve. That means that the function goes as z to the n on this thing. And then you've got another one here, zeta 2, which goes as w to the m. When we go to the point of intersection, this becomes an an plus m minus 1 singularity, which is associated with an order of vanishing of delta of n plus m. So basically, the orders of vanishing are going to add at these intersection points, giving us a much worse singularity. At those points, we're going to get, in this case, for instance, bifundamental matter. And we can kind of schematically draw it like this. Let's say we have an A2, and it hits an A3. Then it's like having another point that gets added in, and we get an A6. So this is an SU3. This is an SU4. These things combine to an SU7. And this is really as if we had an enhanced symmetry at this intersection point, which was like an SU7 symmetry. And so we have SU3 living here, SU4 living here, and the stuff here is in the bifundamental. So that's a heuristic way of thinking of where these bifundamental representations are coming from. It's like they're coming from an adjoint representation of the enhanced symmetry group at this point. So this is like what we saw in the intersecting brane model. We have new matter coming from the intersection. Yeah, Tom.
Chiral, right?
Yes, it's chiral matter.
Yeah. So if you only have one of them, not both.
Yes, that's right. You just have.
The question I was going to ask is what determines whether it's an NM bar or an M bar?
So I'm a little confused about this too. And there's actually some subtlety here, which is related to the fact that F-theory doesn't quite completely reproduce what we can get in heterotic. In the heterotic picture I gave you a minute ago, we could produce models with different combinations of NM bars and NMs. And I don't know how to get that in F-theory. I think that may be related to turning on G-flux. So there's something here which F-theory is not able to do as generally as heterotic, and it's precisely this question. Your question is an excellent one. And I wish I understood a little bit better what the correct answer to it is. But there are, although there are things which are limitations, as I just mentioned, there are much more general things we can do. In particular, imagine we have three curves intersecting, an A1, an A2, and an A4. We can add in a dot like this, and we can get an E8 enhanced symmetry. And this gives us some matter which transforms in three different gauge groups. This will transform in an SU3 cross SU2 cross SU4 gauge group, not something you see in the heterotic construction. So it's much more general in the sense that you can get all kinds of exotic matter appearing in this kind of way. There's other kinds of matter which appears in other ways. It's not all from localized singularities. In particular, adjoints appear from the genus of the curve, which, remember, I wrote down this famous adjunction formula yesterday, which is kind of useful here. 2g minus 2 is k dot c plus xc dot c for a divisor. So it's not just xc dot c, but it's also how xc intersects the entire k that determines g and therefore determines the number of adjoints. There's other symmetric representations and things also appear in slightly more complicated ways. Something I should emphasize is that the possible singularities you might get are not completely classified. There's some partial classification, and most of the commonly found matter is listed, but there are some things which are not understood about the classification, or at least people have not gone through completely and analyzed all the possible singularities, and I'll come back to that in a bit. Questions? Yeah?
Do you have to worry about some kind of tachyon condensation? Or?
Because we're only looking at supersymmetric models where the total space is Calabi-Yau, we don't. If you tried to do something non-supersymmetric, you would certainly have to worry about that. But I don't know how to do F-theory in a non-supersymmetric framework. This is a triple intersection of divisors. That's right. This would be an enhanced symmetry coming from three divisors all intersecting at a point.
Okay, so this is like the E6 point.
It is like that. That's right. Yeah, people use this recently in F-theory constructions in 4 dimensions to try to get the right Yukawa couplings and things like that. You can see this as like a string junction. That's right. That's right. So right now I'm enjoying doing it in 6 dimensions because we can one by one put additional pieces of structure in, and here we can put in matter without having to worry about some of the additional complications that we would get if we went down to 4 dimensions. But if you see talks on 4-dimensional F-theory, they'll almost certainly be doing this plus other stuff. Okay. So the one nice thing about 6 dimensions is that in 6 dimensions, we know essentially what all the possible bases are. As I said, that's not true in 4 dimensions. In 6 dimensions, the base either has vanishing canonical class, in which case it's a K3 or an Enriquez surface, which is like a Z2 quotient of a K3. If there's a vanishing canonical class, there's no discriminant locus. It's just a geometric compactification and has higher supersymmetry and is not so interesting. So the only other possibilities are that the base is a P2 complex projective space, two-dimensional. One of these things called Hirzebruch surfaces, FM, which I will tell you more about in a moment, or a blow-up of one of those things where you take a point, replace it by an S2, and continue doing that some number of times. So this is essentially stated in Morris and Vafa. This follows from, there's a beautiful classification in mathematics, which I only partially understand, of complex surfaces using the notion of minimal surfaces. And the basic idea here is that you can take any surface, and if it has an exceptional cycle, which has a, c dot c is -2, which is a sphere, you can blow it down, and you can keep doing that until you get to one of a class of surfaces called minimal surfaces. And this minimal surface theory classifies those minimal surfaces in most cases in a fairly complete way. In the case where we're allowed to have an elliptic fibration, which is Calabi-Yau over it, the minimal surfaces are just P2 and FM. And so all the surfaces that you can use as the bases are those things or blowups if the base is smooth. It is possible that there are non-smooth bases, which we don't really understand, which could give alternate theories. And that's an interesting thing to research, but I don't know more about it than that. Let's talk briefly about P2, because it's easy. In P2, there's only one element of H2. It's the hyperplane, so you just do an arbitrary hyperplane. Any divisor is a multiple of H. H squared is 1. The canonical class is -3H, and therefore squares to 9. And as we'll see, all the models with t equals 0 live on that base. I'll tell you a little bit about Hirzebruch surfaces. They're kind of simple. They're just P1s, S2s, over S2s with some twisting. It's like taking a sphere, putting a line bundle over it, and twisting it some number of times, and then projectivizing it or compactifying it with a certain first Chern class. So for instance, F0 is just P1 cross P1, no twisting. F1 you can get by blowing up P2 twice. It's just a P1 over P1 where you twist once. F2, as you know, if you've ever tried to comb the hair on the hairy hedgehog? If you try to comb the hair on a sphere, you will find that there are 2 points where you can't get the hair to all go in the same direction. That's because the first Chern class of T star of P2 is 2 or -2. F2 is given by compactifying that line bundle over P1. So we can write down a convenient basis for the divisors on these Hirzebruch surfaces, so we can actually talk about these compactifications. There's one which we'll call dV, which is a section. So we have a P1 over P1. Over P1. So there's a copy of P1 here everywhere. dV is like a section, and ds is like a fiber. There's dV. ds is like a certain fiber here. dV, they intersect each other at one point. And because of this twist that you're putting on the P1, the more of a twist you have, the more times dV will intersect itself. So dV has a self-intersection -m. So for instance, for F2, it intersects itself twice. Those are the points where you can't comb the hedgehog. And here's a schematic picture of dV and ds. dV and ds intersect at one point. ds doesn't intersect itself at all. You can just slide it around on the P2. Sorry? This is for FM. I'm taking a particular class of surfaces, and I'm telling you essentially what the intersection form on these is, because we're going to turn this into a lattice, as I like to do in these lectures. This is a lattice, and dV and ds are generators of a two-dimensional space here. And there's a condition on the irreducible effective divisors, which is basically that it's either dV or dV plus bds, where b is bigger than m times a. And then we have a formula for the canonical class, which is some combination of dV twice dV plus 2 plus m ds. This is the thing which tells us how curved the thing is. Notice that the more we twist this thing, the more ds's we get in our curvature, basically. Okay? So there's a little bit of math there. I'm just thinking about when I'm going to end. If I run 10 minutes over, is everybody going to be okay? Okay, you can leave if you don't like that. I mean, whenever you like. I think we should be able to wrap up in that by 10 minutes after. Okay. So let me show you a few examples. Now that we've got all these sort of pieces together, the machinery, let's do a couple examples. Let's take this example we talked about this morning, SUN with no adjoints, no antisymmetrics, and just fundamentals. Right? We showed that that satisfies anomaly cancellation. Let me show you a place where you can realize that in F-theory. We're going to do it on F2. And in a few minutes, we'll see that actually this is the unique place you can get this in F-theory by explicitly doing this map up from the data to F-theory. But for now, I'll just tell you where it comes from. If we take that formula for the canonical class, the total curvature is 2 dVs and 4 ds's. That means by the Kodaira formula that the total discriminant locus has to be 12 times that, which is 24 dVs and 48 ds's. I'm going to wrap n divisors on n 7 branes on the divisor C, which is dV. So n dV is a nice effective divisor, so we can wrap n on this thing. This is actually an irreducible effective divisor. We wrap n 7 branes on this guy. So we get an SUN gauge group on this divisor. And the residual locus, the part of the divisor which isn't wrapped up in this enhanced symmetry, is everything here in the total delta minus n times dV. So it's 24 minus n times dV plus 48 ds. And to compute the amount of fundamental matter, so here's the picture. So we've got n dVs. And then we've got this residual locus y, which kind of goes around like this. It doesn't have any non-abelian gauge symmetry on it, but every time it hits dV, it changes the SUN to an SUN plus 1 through this. It adds another point on the Dinkin diagram, giving us a fundamental. So we get a fundamental here at every point of intersection. So to compute the number of fundamentals, we dock C into Y, and so we dotted in dV squared is minus 2. So dV dotted into this is minus 48. This is plus 48 vanishes. Minus 2 times minus n gives us 2n. So we get exactly the right matter content to satisfy the anomaly condition. And I told you that the number of adjoints is given by the genus, where this is the adjunction formula. We dot dV, this guy, into k plus c. K here is this. Subtract it's minus this, so it's minus 4 ds minus 2 dV plus a dV is this. dV dotted into this is, in fact, 2. So this thing gives us a, I've got a minus sign there. Something's wrong. dV.ds is 1. That's minus 2. That's plus 2. That should be minus 2. OK. So that's minus 2. Good. So there's an example. There's your first F-theory compactification to 6D. We get an SUN gauge theory with 2n fundamentals. There are, on Y, there is not a singularity in the full space. There's only a singularity in elliptic fibration. It's like those extra points we had on S2. They don't contribute to the non-abelian gauge group. There are 7 branes there, but they're not going to carry any non-abelian chart, any non-abelian gauge group structure. There's some U1s that may appear there, but again, I want to avoid U1s because they can be lifted. So sorry, the answer to your question is yes, there are 7 branes wrapped there. There are 7 branes there, but they're all separated from each other. That's right. So nothing's hitting each other. So we can do a similar thing with a more fancy thing coming from heterotic. We can take E7 cross E8. We can embed it on F12 by putting E8 on the dV, E7 on dV plus 12 ds. And if you look at the intersection form, you get 0. More generally, and this is worked out in Morris and Vafa, if you have an E8 cross E8 theory with 12 plus n instantons in the first E8 and 12 minus n in the second one, it goes to Fn. So I'm just giving you some examples of F-theory constructions. These can get very complicated. Aspinwall and Morrison found this gauge group, E8 to the 17 cross F4 to the 16 cross G2 to the 32 cross SU2 to the 32 in a model with 192 tensor multiplets associated with the Calabi-Yau, the elliptically fibered Calabi-Yau of largest known Euler character. This has a sort of exotic heterotic dual, which is very singular. So there's all kinds of crazy stuff. So how can we organize all this? It seems very hard. I've given you some sense of what all the bases are, but there's no complete mathematical understanding of the set of multiply blown up bases and their effective divisor classes. That's a problem which is not fully solved. Because after you blow up 9 times, note the 9, funny things start to happen, and suddenly you have infinite numbers of, the space of effective divisors becomes like a cone with an infinite number of walls, which is hard to classify. So how do we organize all this? Well, the way we can organize it all is by using the data from the low energy theory. So in overtime, let me go back to the low energy theory and show you how to get from the low energy theory data of the anomalies back into F theory. So let's try to identify the F theory data and how it relates to the low energy data. The number of tensors is h1, 1 to the base minus 1. K squared is therefore going to be equal to 9 minus t. So one way to see this is that k squared is 9 on the P2, and every time we blow it up, we subtract 1 from k squared. So you can see that after you blow up 9 times, k squared is 0. Each gauge group factor, gi, is going to be associated with some singular divisor xi. Remember that in the anomaly polynomial, we had a vector bi in the 1, t space associated with each of these singular divisors.
How does the first equation come about? A is equal to h1.
Because you get a tensor multiplet from each one of these guys, and you can write k squared in terms of this guy. The easy way to see it is just take the statement I made that the k squared is decreasing by 1 every time you blow something up, and start on either P2 or FM. FMs all have k squared equals 8, which we can prove from the formula I gave you, and P2 has k squared equals 9. And then you can just...
How to get tensor multiplication in that sentence?
Good. Every time you blow up a point, you get an extra tensor multiplet. It comes from when you blow up a point, you get a new cycle, and that gives you a new element of h11. That is associated with a tensor multiplet, which can be seen in various ways, but one easy way to see it is that the intersection form on this thing picks up another negative component. Physically, what's happening is there's a class of phase transitions, and this is jumping ahead a little bit, but there's a class of phase transitions where you trade 29 hypermultiplets for a tensor multiplet. And when you blow up a point on the base, you are connecting regions of the moduli space with one number of tensor multiplets to regions with another number of tensor multiplets. Once I tell you this map, you'll see how this works. There's a match between the intersections. I mean, in the F theory construction, we know that when you intersect 2 divisors, you get some matter. We know from the anomaly cancellation condition that when you intersect 2 Bs, you get some matter. So it was pointed out by Sadov and Grassi and Morrison that these guys exactly relate. So we can actually relate the low energy data to the data of F theory by just mapping A, which is a vector in this abstract 1, t space, into the canonical class, mapping Bi into this part of the divisor locus, of the discriminant locus. That gives us a map from the lattice lambda into H2, and along with that we can map J into J. So to be a little more concrete about it, if t equals 1, remember we can define B as in terms of alpha and alpha tilde, that maps into this thing living in Fm. So this is an explicit formula telling us how each gauge group is associated with a divisor class in F theory. And if we look at what happens to A, if we take A as -2, map it through this map, this precisely gives us the canonical class that we described earlier. So A is the same as the canonical class. So now we can see very clearly why this is true, because A squared is 9 minus t, the canonical class squared is 9 minus t, and we identify those two things. So this gives us a way of reading off all the data we need for an F theory construction from the low energy data. You just read off what the anomaly polynomials are, figure out how to solve them in terms of A's and B's, and then map them into the divisor classes of the base according to a formula like this for t equals 1. Okay. Give you an example. So the statement now is if we map the lattice lambda into H2 of BZ, this is a lattice embedding which determines the topological F theory data, not necessarily uniquely. Once we get the right topological data, I've been kind of ignoring the Weierstrass model. You have to check to make sure that you can actually build a Weierstrass model. In many cases, that seems to work, but we don't have a proof that it always works. So a lot of everything I'm saying here now is stuff that we've been doing with Vijay Kumar and Dave Morrison. Some has appeared, some will appear. Let's go back to our example of t equals 1 and SUN with 2n fundamentals. We know that the B vector is 1 minus 1, right? Remember we computed that this morning. And 1 minus 1 under this map, if alpha is 1, we get, I guess alpha would be 2 then. So alpha is 2, so this is 1 times this thing plus 1 times that thing. We get dv plus m over 2 minus 1 ds. That's supposed to be an effective divisor, which means that this number here has to be bigger than or equal to m, or else 0. It can't be bigger than or equal to m, so therefore it has to be 0. So this maps to dv, and therefore this has to be 0, so m equals 2. So the only way to realize this model is by realizing the SUN on n copies of dv in the Hirzebruch surface F2. So this gives us a way of taking a low energy theory and figuring out where it comes from in F theory. So we took all 70,000 t equals 1 models with product gauge groups of SUN and these kinds of matter and checked that they all seem topologically consistent with F theory. Then there's this question of whether there are Weierstrass models. You can show that the number of degrees of freedom that you have in choosing your Weierstrass model is precisely the same as the number of available moduli. So this seems plausible that it will work. Interesting things start to appear. There are exotic matter representations that you can find. If you try to classify solutions to the anomaly equations, there's an sorry, I didn't write it down, it's SU8. There's an SU8 model with this matter, including a 4-fold antisymmetric, which takes up 243 of the degrees of freedom in F theory. What that means is, this is speculated, that if this is a correct model in F theory, it means that if you tune 243 of the 244 degrees of freedom available to you in the polynomials describing the elliptic fibration over, in this case I think it's F1, you should get this singularity structure. Nobody's ever found this singularity structure. As I say, the singularity structures giving matter in F theory are not completely classified. This suggests that maybe this is one of the ones that hasn't been found. Nobody's ever seen one of these models in string theory, but it might well be there.
Can you show up in heterotic these exotic representations?
No.
So,
There's threefold antisymmetrics which do appear. There may be a very singular limit of heterotic where you can find such things.
how do you calculate their existence then? Because it's not derivative string theory and there's no heterotic.
I've calculated their existence by anomaly cancellation. The conjecture is that these are realized in string theory. We know that there's a low energy theory. It seems to fit that it would fit in string theory. However, there are other things which don't fit in string theory. For instance, I mentioned this SO8 cross SU24. You can embed this using this embedding formula, the one that I said we found that we couldn't realize using heterotic theory. You can embed it in F theory, but the divisors don't quite work out. Maybe this is some new version of F theory where the Kähler class has moved outside the usual Kähler cone, but it might not be. It might be a sick theory. There are other models. For instance, if we have SU4 with one adjoint, these are pretty rare and sporadic at t equals 1, but there's a few of these models which you can construct which satisfy all the known consistency conditions, but this one, for instance, can't be embedded into a unimodular lattice. And all the intersection lattices for the bases of all the Hirzebruch surfaces and their blowups are all unimodular. So that means we have some models that we can't realize in string theory, and that raises the question of whether maybe string theory, maybe low energy physics should impose an additional constraint that there should be some underlying unimodular lattice here, like there is for heterotic compactifications. Okay, I'm sort of wrapping up here. I mentioned these infinite families. These things don't work in F theory, and for instance, at t equals 9, you can use the Kodaira constraint to prove that they don't. We don't have an analog of the Kodaira constraint in the low energy theory. Okay, so let's wrap up.
What about the possibility of duality? I mean, the models that you don't find in string theory.
It's possible that they could be given by another string theory. That's correct. Let me show you the picture. This is the picture of what we know, where the vertical columns are the t's. There are these phase transitions, as I say, that connect the little moduli spaces at one t to the next. Everything seems to be basically connected between these different little regions, which represent some particular set of gauge groups and matter content. At small t, almost everything, the green is what we can realize in F theory. The red is what we can't rule out, right? This is the space of supergravity theories that we can't rule out. At small t, there are only a few things that we can't rule out that we can't get in F-theory. You're absolutely right. Maybe those represent new string theory compactifications. But maybe there are new low energy constraints. The challenge to all of you is to try to take some point in this space and either try to put it in the green by finding a string realization, or find some way in which it's a quantum inconsistent theory and find a new cut by which we can cut down on the red junk. So each of these things is a little continuous moduli space connected by various kinds of transitions, and this is just what I was saying. Can we find either new consistency conditions, or can we find new string things? We would also like to have a more systematic charting of the region, but the message I want to get across is, well, in 8 dimensions, we had a full picture of what you could get from string theory. In 6 dimensions, we have a pretty good sense of the outlines of that, but there are still open questions. So let me conclude. In 11D and 10D, consistent supergravity is the same as supersymmetric string vacua. For those interested, after I wrap up, I'll show you the result, which I mentioned at the beginning of the week, I think has held up. So I'm happy to tell you that I think that we've ruled out the U1 to the 496 and the E8 cross U1 to the 248 theories with Oliver and Ellen Adams, which seem to be inconsistent quantum theories. So we can confidently state that in 10D, supergravity is the same as a set of string vacua. In 8D, we can get a bunch of vacua, but it's much smaller than the set of theories that we can't rule out. So are there other constraints? In 6th dimension, we have this general sense, which I just described. We can either find new constraints or vacua, and we only have some patchy understanding in 4 dimensions, although there's lots of beautiful work in 4 dimensions. From this global point of view, we still can't quite fit it all together into a global picture. The main message I would like to convey here is that string theory definitely seems to constrain low energy physics. I think I've given talks over the years where I've said various things about this, but from all these pictures, it's quite clear that the set of low energy theories that you can get is very constrained in string theory. Now, some of those constraints are visible in the low energy theory as anomaly cancellation, but I would still say that those are constraints associated with the set of theories you can get from string theory. In some dimensions, we can see those clearly with anomalies. In other dimensions, like 8, we can't see them clearly, but perhaps we will find another way of determining those constraints. Yes?
I hope you have been looking at only the small quantum string theory where you have control over. How can you draw that?
Well, I'm talking about all supersymmetric solutions.
Right, but I thought there are strong coupling regions, for example, you don't have control.
Well, I think that in 10 dimensions, I think we have a complete control over the situation. In 6D, string theory is definitely strongly constraining things in the sense that the anomaly constraints that I showed you already strongly constrain things. Yes.
There are parts that you couldn't constrain by anomaly and you couldn't get by F-theory.
That's correct.
That part you might think that there may be phase junction to where you have.
Those could be valid. Even if all those things are realized in some other aspect of string theory, I would still say that string theory is strongly constraining things. Well, I guess I would say anomaly constraints maybe can be thought of as a window on some of the constraints that come from string theory. And maybe we need other windows on those constraints. It may be that eventually we'll have a whole set of constraints which determine a set of theories which can be shown to be the only set of theories that are not inconsistent from the low energy point of view. And maybe that'll be identified with string theory. I still think that those are strong constraints coming from string theory, even if we can understand them from the low energy point of view. In fact, it may be that string theory will be helpful in unveiling those other constraints. The vacuum constructions become more complicated in lower dimension. I don't think anybody would quibble about that. Making a global picture of 4D is a challenge, and I think that the 6D story is a good place to learn about constructions in general and getting a global picture. And I'm sorry to run over, but thanks a lot for all your questions. I enjoyed the lectures and enjoy the rest of the school.